We've started off talking about the derivative at a certain point, that is f prime of a. That's the derivative, or the rate of change, or in other words, the slope of the tangent line at a particular point. Now what we want to do is talk about the derivative as a function, that is f prime of x. This definition is going to be very similar to the one we did before, but instead of a, we use x. It's the limit as h approaches 0 of f of x plus h minus f of x divided by h. This is true if the limit exists and x is in the domain of my function f. Let's do an example. Let's find f prime of x if f of x is equal to negative x squared plus 6x. And I'm specifically saying by the definition of the derivative. If on an exam you already know the shorthand method of finding a derivative and you simply write down the answer, you're going to get 0 points for a question that says by the definition of the derivative. You must, to get any credit whatsoever, you need to write this out. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. The other thing you need to do is go through the algebra in order to prove this. The very next lecture after this will show you some much easier ways, but you will have to do this at least once on the first exam, as well again on the final exam. Let's go ahead and plug in x plus h into my function. When we plug in x plus h and x into my f of x plus h and f of x, I get this. Now I carefully do some algebra. Make sure you multiply the x plus h all squared properly. And I already see some things adding to 0 and some more. And we're going to get it down to this. Oh, but I've been very, very sloppy. What have I forgotten? This isn't equal to this fraction. I need to make sure I'm always talking about the limit as h approaches 0. Because if I forget that, I'm going to have a final answer with h in it, and that would be incorrect. Alright, I see that my h divides from my numerator and denominator, and because what's left is a polynomial, I can do direct substitution, so this limit is simply negative 2x plus 6. So f prime of x, when f of x is equal to negative x squared plus 6x, is simply negative 2x plus 6. Instead of talking about f prime of x, there's another way of talking about the derivative, and that comes from where that slope of the secant line started with. Let's say I took 2 points, and if I wanted to find the slope of that secant line, I would take that line and I would look at the slope. And the slope, of course, is just the change in y over the change of x. Delta often means change. So delta y is the same thing as saying y2 minus y1. If we remember, our slope of our secant line is f of x plus h minus f of x divided by h. Instead of that h, if I think of that h, which would be represented there as delta x, then I can rewrite this as such. I can write this as f of x plus delta x minus f of x divided by delta x. That numerator is simply the change in my function or my y, or delta y divided by delta x. If I wanted to talk about my tangent slope, I would take the limit as delta x goes to 0 of the slope of my secant line. As I do that, it's the limit as delta x goes to 0 of delta y over delta x, or we write that as dy over dx. So let me write a few different ways we can talk about the derivative. We've already talked about f prime of x, and now I've mentioned dy dx. You could also call this df dx, or ddx of f of x. If I wanted to talk about at a point, let's say a specific point, point A, I would write f prime of a. This is called, by the way, prime notation. We could also say y prime of a, and I guess I missed that as another way of talking about the derivative, y prime of x. Again, that one is also prime notation. Or I could say df dx evaluated at x equals a, or dy dx is evaluated at x equals a. That notation is called Leibniz notation. This notation was introduced by Gottfried Wilhelm von Leibniz, one of the people who invented calculus back in the 1600s. Let's do 2 quick examples. Find dy dx if y equals f of x equals square root of x. Dy dx is simply the derivative, And again, in this video, I'm always talking about by the definition of the derivative. And I'm going to use this definition, and I get the square root of x plus h minus the square root of x over h, and that's the limit as h approaches 0. So again, I'm going to have to multiply the numerator and denominator by the conjugate of my numerator. And when I do that, I get this, which simplifies to this. And if I go ahead and divide the h out of the numerator and denominator, being sure to keep the 1 in the numerator, let's see, when h approaches 0, I think this becomes simply 1 over 2 square root of x. Notice I could additionally ask you for the slope of the tangent line at 4, 2, and then I'm expecting you to understand that the derivative is simply the slope of the tangent line. So what I'll do is I'll take my dy dx, evaluate it at x equals 4, and I'll get an answer for the slope of 1/4. Then I use my point slope form of the line, and if I multiply this out, I can get it in slope-intercept form and get that as my final answer. Here's another example. This time instead of f of x, I'm doing f of t, but I don't think this would throw anybody off too much. So I would have f of t plus h minus f of t divided by h, and the limit of that as h approaches 0. And let's go ahead and plug in my function. Again, I'm going to multiply the numerator and denominator by the lowest common denominator. And then from here, I get to here. And finally, I get it to a point where I can see I can factor out a single h. When I do that, I can divide out that h. And now I can let h go to 0. In this case, I get that the limit is equal to -2 over t cubed.